Hi, this is lesson 4 of Unit 7 in chemistry. And for this lesson, we'll be focusing on acids and bases as well as how to figure out the strength of an acid or a base. For our lesson objective, students will learn about the pH scale and how to use it to classify a solution as either an acid, base, or neutral. Let's go ahead and get started.
So let's begin our discussion of acids and bases. The word acid comes from Latin acidus. That means sour. And if you think about it, yeah, that describes the taste of a lemon, which is very sour. And a lemon is acidic. Now, bases, on the other hand, they taste bitter and they're soapy to the touch. And the reason why they're soapy to the touch is because a base will go ahead and turn oil into soap. So if you've ever been cleaning, then and you have your hands exposed to a cleaning solution, which they tend to be basic, they'll feel slippery and soapy. That's why they're turning the oil from your skin into soap. As a matter of fact, in the old days, that's how soap used to be made, from oils or fats. So mainly they're from whale fat. So you see the picture on the bottom left. It's a little bit grotesque, but that is someone cutting into a whale, and they will get the blubber, which is the fat of the whale, and they will mix it with a strong base, and they will go ahead and produce soap from that process. Now, if you're thinking, would the soap be clean? Would it smell like whale? No, it would just smell like plain old soap. Now, on the pH scales, we can differentiate when something's acidic versus something that is basic. The pH scale goes from 0 to 14, where 7 is the middle of it. It's a neutral compound. Now, going from left to right, we start at 0, battery acid, very powerful. Then stomach acid, 2 would be a lemon juice, a 3 would be vinegar. Tomato, you find it at 4 on the pH scale. Coffee is slightly acidic at 5. Milk is slightly acidic at 6. Number 7, we have water, which is neutral at that point. Now that we keep it rising on the pH scale to number 8, we get to slightly basic. And as we progress, we're going to be more and more basic. So number 8, blood, and then followed by baking soda. Stomach tablets like antacids will be number 10. Ammonia solution, which is used for cleaning, is number 11. Soap is used for number 12. Bleach for number 13. Now, you may have noticed that you have baking soda, ammonia, bleach, soap. A lot of cleaners are basic. And finally, all the way on the far right, you'll find drain cleaner. That's a very, very powerful base. Now, another word for basic is alkaline. So you notice way at the bottom, on the bottom left, they have acidic. And opposite of acidic, they should have basic, but instead they chose to write alkaline, which is another way of writing basic. All right, so let's get more in detail about what is an acid. So we know that an acid, how it tastes sour, and that's where the name comes from. But what exactly is an acid? So we're going to look at two competing definitions of what is an acid. The Arrhenius theory says any substance that releases a hydrogen ion in water, you refer to that as an acid. The Bronsted-Lowry theory, he states that any substance that donates a proton, that's an acid. If you go ahead and think about it for a second, a proton is the same as a hydrogen ion. So they're both the same, just slightly different method. A hydrogen ion, think of a hydrogen atom has a proton in the middle and the electron on the outside. So how do you turn a hydrogen atom into an ion? You remove that electron. So what's left behind? The proton at the center of the atom. So therefore, hydrogen ion is the same as a proton. Examples there, we have stomach acid, lemon juice, and vinegar. They're all acidic substances. Bases, on the other hand, their definitions for Arrhenius theory states that any substance that releases an OH, as a hydroxide ion, into water, that is a base. The Bronsted-Lowry theory is a little bit more open. It says any substance that can accept a proton. So if the acid donated a proton, the Bronsted-Lowry states that the base accepts a proton. For example, so bases, notice I have 3 cleaners there: all-purpose cleaner, oven cleaner, baking soda, which could be used as a cleaner, and Nair, which is hair remover. Now, a substance that can act as either an acid or a base is said to be amphoteric. So an example of that would be water, probably a really good example of an amphoteric substance, because in some reactions you might see it as acting as either an acid or a base. Also, polyprotic acids. What is a polyprotic acid? These are acids that can donate more than one hydrogen atom. For example, sulfuric acid right there, phosphoric acid, H2SE would also be another example of a polyprotic acid. Anhydrates. An anhydrate is a substance that becomes acidic or basic when mixed with water. So before, they're neither acidic nor basic, they're neutral, but once exposed to water, they'll go ahead and become either acidic or basic. Well, that is the main source for acid rain, anhydrates. Anhydrates such as carbon dioxide, sulfur dioxide, nitrogen dioxide, those are byproducts of combustion in maybe from cars or factories, and they'll make that, and it's a gas, and it'll go up to the rain clouds and mix with the water in rain clouds, and it'll come down as acid rain. On the picture on the right, you can see the effects that acid rain has on structures, particularly stones. The picture from the left-hand side here, was taken in 1908, and the picture on the right is 60 years later, 1968, and you can see the effects that acid rain has had on this statue, making it to the point where you can no longer see the features. Now, here's some of examples. So for acid rain, I mentioned carbon dioxide will mix with water to give you carbonic acid. And here SO2, sulfur dioxide, would mix with water to also produce this acid as well. And pollution from cars and factories, mixing them with rain clouds. Here we got the product. They'll produce acid rain, which could collect in the ground. It could affect how well flowers grow, or they might not grow at all. And it could also produce mutations in animals. As you see this little frog right there, the left leg is highly deformed, likely because of some sort of pollution in the water. Now let's switch gears a little bit and talk about what is a conjugate acid. So if you have an acid base that react, you're going to create a product. The products are called the conjugates. Now you have to identify as a conjugate acid and a conjugate base. The conjugate acid is the particle obtained after the base has gained a proton. On the other hand, the conjugate base is the particle remaining after the acid has donated a proton. Now, those definitions are a little bit tough to memorize. It's a lot easier to just look at the reaction and try to understand what exactly is going on. So let's go ahead and take a look at example 1. Says identify the conjugate acid base pairs in the following reactions. All right, so let's just focus on reaction A. You have NH4 plus OH will give you NH3 plus H2O. So ammonium ion plus hydroxide ion yields ammonia plus water. All right, who's the acid, who's the base? First of all, let's find the pairs. All right, so who are the pairs? Let's look at the first one, ammonia, NH4. You see this nitrogen. And now on the other side, you see nitrogen as well. There's our pair. So I'm going to go ahead and draw a line stating that these guys are the pairs. On the other hand, let's look at the oxygens here and here. There's our other pair. What about the hydrogens? Oh, we're going to be looking at those. I'm going to keep careful count of the hydrogens. Now, who is the acid? Who's the base? They're going to be on the left-hand side of the arrow, on the left-hand side of the yield. That's the actual name for the arrow. So we're going to count how many atoms, how many hydrogen atoms each one of these reactants have, and then compare it to the product. And if compound has less hydrogens, then that is your acid, because the acid gives away the hydrogens. So let's look at NH4. I'm looking at that one first because it's the first one listed. NH4, how many hydrogens does it have at first? The nitrogen, 4. Now you look at the other side. How many are left over? 3. Does it have more or less hydrogens? It's got less. It gave away one of its hydrogens. So therefore, we can go ahead and look at the NH4 and immediately identify it as an acid. So I'm just going to put A, meaning acid. So the NH4 is our acid. All right, if that's the acid, then what is the NH3? It must be the base. In this case, it's referred to as a conjugate base because it's on the right-hand side, it's on the product. So I'm going to label that for CB for conjugate base. All right, so we identified 2 of them. All right, automatically I can say, well, if the NH4 is the acid, then the OH must be the base. But let's take the time to actually look at the number of hydrogens. Remember, an acid gives away hydrogens, a base must take in hydrogens. So if the number of hydrogen increases, then that is our base. And let's count them. We only have 1 hydrogen here on the left-hand side, and on the right-hand side, we have 2 hydrogens. So therefore, the number of hydrogens increase. So definitely that is our base. I'm going to label that as our base. So if this is a base, then this must be the opposite pair, must be the conjugate acid. So we have identified everyone here. I see the acid base, which acid base are always on the left hand side, and conjugate acid, conjugate base, which are always on the right hand side. All right, now let's go ahead and take a look at B. Same rules apply. I want to look, let's see. Letter B, we have HBr. So here and there. So those are my pairs. I'm going to look at both of those. And here we have oxygen and oxygen as well. So that's my other pair. So I'm going to take a look at both of those. All right, for the HBr, we have how many hydrogens? We have 1. And now how many hydrogens do we have on the right side? We got none. So we went from having 1, it dropped to having 0. So if it has less hydrogens, again, you refer to that as your acid. All right, so I'm going to label that as acid. And if that's the acid, then the matching pair on the other side must be its base. So that's a conjugate base. I'm going to label that. There's my answer, conjugate base. Now, let's take a look at the oxygen. Initially had 2 hydrogens, and now it has 3 hydrogens. So if the number of hydrogen increases, therefore, what do we get? That is a base. And a base will go ahead and accept hydrogen atoms. So therefore, I'm going to label water here as our base. And therefore, what's the matching pair? Must be its acid. So this, the H3O, the hydronium ion, that's its name. We're going to label it as our conjugate acid. All right, so that's the setup. Now notice that I have acid on both A and B, the very first element. And sometimes students develop the idea, well, is the first one always the acid? No, that's not the case. You actually got to count, did it go up in hydrogens? Well, then that's a base. Did it go down in hydrogens? Well, then that's an acid. So keep track of the hydrogens. In problem number 2, A and B, we're going to look at much the same, figure out who's a conjugate acid, conjugate base. All right, so let's see. Here we have HSO4 as well. See how they match up. So now, oh, those are my matching pairs. And here's same thing for oxygen and oxygen. All right, so let's count. How many hydrogens here? It's only got 1 for the HSO4, -1. And here it's got none. So it went down. We used to have 1, now we have none. Again, this must be our acid. And the other one must be its matching pair. So therefore, it's got to be the conjugate base. So that's our answer. Now, let's look at the oxygen. It had 2 hydrogens. Now, on the right side, it's got 3. So it went up. So therefore, that must be our base because it has more hydrogens now. And therefore, this must be our conjugate acid. That takes care of part A of example 2. Now, let's take a look at part B. So we're going to do much of the same. We're going to compare. Let's see. That's CO3 and that's CO3. All right. So let's see. What do we have here? These two match up. And this one has an N and also has an N on the right-hand side. So these two match up. So those are the pairs that we're looking at. So let's begin with HCO3. It's got 1 hydrogen. But now you look at the right-hand side. It's got 2 hydrogens. So it went up. So therefore, our HCO3 must be our base because it increased the number of hydrogens. So that is our base. Therefore, what's the matching pair? Oh, it's the opposite, conjugate acid. Next, NH4. We have nitrogen here on the left-hand side. It has 4 hydrogens. On the right-hand side, it's only got 3 hydrogens. So it went down. So what do you call that when it goes down? You call it the acid. And what's the matching pair? That is the conjugate base there. That will be the answer for the NH3, which is its common name is ammonia. All right, so that is the process of figuring out who are the acids and who are the bases and who are the conjugate acid and base pairs. Again, acids and bases are always on the left side of the reaction, and the conjugate acid and conjugate base are always on the right-hand side. Now, how do you tell if an acid is either strong or weak? For example, we have HCl here as a first example. I want to say that that is a strong acid, but here we have HF, and we're going to say that is a weak acid. And you might be looking at those like, but when I look both of these, they both release a hydrogen ion. So if they're both releasing the same atom, the same ion, why is one strong and the other one is weak? The answer has to do with how much is released. So for example, HCl dissociates, that means that it breaks apart like it did here, dissociates into ions completely, all of them, so 100%. So if we start with 100 molecules here, at the end we're going to have 100 molecules have separated. All of them will separate. So we'll end with 0 on the left side, and we end with 100. All right, now, but HF will only dissociate slightly, a little bit. That means that it's got a stronger bond between the hydrogen and the fluorines. It's got a stronger bond, so they're going to stick to each other. So if we start with 100 here for our reactant and 0 for our product, and then once you put the HF in water, it's going to dissociate, but only slightly. Maybe you'll end up with like 80 molecules of HF here, and the ions there only be 20. So notice the difference versus this at 20, that's 100. And again, why? It has to do with the attraction between the molecules. If the attraction is very strong, they're going to stick to each other, so only a few break apart, versus for HCl, it's going to have a weak attraction, so therefore we put in water, they're just all going to break apart, releasing a lot more of the H plus and making that the strong acid. So the last bullet at the bottom says the bond strength determines the amount of dissociation. A weak bond will break apart and will dissociate a lot, giving a strong acid. A strong bond, those atoms are going to stick to each other, releasing very few H pluses. Therefore, that is a weak acid. Now, there's different types of acids. There's binary acids and ternary acids. We're going to go ahead and begin with the binary acids. What's a binary acid? Binary's got 2 elements. That's it, only 2 elements. So binary acids are those that contain only 2 elements, hydrogen and then something else. X means just another element. Hydrogen and some other elements. Now, how can you tell if a binary acid is strong or weak? Was fairly simple. There are only 3 acids that are binary and strong. Who are those? They are HCl, hydrogen chloride, HBr, hydrogen bromide, and HI, hydrogen iodide. Those are the only 3 binary acids, that means with 2 elements, that are strong. Those are the only 3 you have to memorize. Everyone else, you say, well, that is a weak binary acid. All right, so that's how you can tell if a binary acid is strong or weak. If it's a hydrogen attached to Cl, Br, or I, strong. Everybody else, say, oh, that's a weak binary acid. The next one's a ternary acid. Those are acids that have 3 elements. And the 3 elements are going to be hydrogen in the front, oxygen in the end, and in the middle, some other element. Usually it's a nonmetal. All right, so ternary acid are those that contains 3. They could have 4 or more elements, but normally 3. All right, so sulfuric acid would be an example. You see that in the picture in the bottom right corner of the slide. All right, now, how can you tell when they're strong or weak? This is the formula. It's a little bit of a math formula. It says strong ternary acids that are identified by subtracting the number of oxygen atoms from the number of hydrogen atoms. So oxygens minus hydrogens. If your answer is 2 or more, 2, 3, 4, 5, then that is a strong ternary acid. But if your answer is 1 or 0, then that is a weak, very weak ternary acid. All right, so that's how you can tell them apart. Again, subtract oxygen minus hydrogen. 2 or more is strong, 1 or less, weak. All right, so that's what you do. So now, in example 3, we're asked, can you identify who is strong and who is weak? All right, let's begin with our binary acids. So binary, they only have 2 elements. So this is binary, and this is binary. They only have 3 elements. All right, so who is strong and who is weak? I'm going to label this one as strong. I'm going to put an S right here. Strong. This is weak. And this one is weak. All right, so that's the answer. Is like, how do I know that? Again, there's only 3 binary acids that are strong. And let's go back to review that. It's either HCl, HBr, or I. Only those 3, Cl, Br, and I. Every other binary acid is weak. So let's go back to the problem. See, there's the Cl. So that's why it's strong. HF weak, H2S weak. But H2S is a binary acid. There's only two elements, hydrogen and sulfur. Some students get confused, like, but isn't there three different elements? H2, there's two hydrogens and one sulfur. That's still a binary acid. There's only hydrogen and sulfur, two elements. All right, so now we got the binary acids out of the way. Let's work with the ternary acids. That's everybody else. So what we're going to go ahead and do is subtract the number of oxygens minus the number of hydrogens. So here we have, no number means 1. So 3 oxygens minus 1, that gives me an answer. 3 minus 1 is 2. Remember, 2 or more is strong. 1 or less is weak. So this guy is a strong acid. This, 4 minus 1, that gives me a 3. So therefore, 2 or more is strong. This is strong. 4 minus 2 gives me the answer is 2. So this is also strong. But 4 minus 3 is a 1. 1 or less is weak. So this will be a weak ternary acid. Let's continue with letter G. 3 minus 3 is 0. So 1 or less is weak for the ternary acids. No numbers 1 and 1, so that's a 0. Again, that is weak. And finally, 3 minus 2 gives me a 1. So 1 or less is weak. So again, notice when you have 2 or more, I said strong for the ternary acids. 1 or less, it's weak, again, for the ternary acids. So that's how you can tell which acids are strong versus which acids are weak. Now let's go ahead and talk about the bases. Most bases can be identified by the presence of a hydroxide. When you see that hydroxide at the end, is a base. All right, so there's only one exception. We'll deal with it a little bit later on. All right, so when you see a hydroxide, you can immediately identify that's a base, that it has a very characteristic OH at the end of it. All right, now how can you tell whether a base is strong or weak? So strong bases are alkali metals bonded to the hydroxide ion. So this is our hydroxide ion. So if you have an alkali metal attached to a hydroxide ion, that is a strong base. On the other hand, if an alkaline earth metal is bonded to a hydroxide ion, it's strong, except for 2 elements, the top 2, beryllium and magnesium. That is the exception. So on your periodic table, where are the alkali metals and where are the alkaline earth metals? The alkali metals are every element in the first column, except for hydrogen, who's not a metal. And the alkaline earth metal is the second column, and every element in the second column except for beryllium and magnesium, which are the first 2, are going to go ahead and form a strong base. Now for our example here, they're asking you identify which of the following are strong bases or which ones are weak. All right, so again, all of these guys are bases, and what is the same thing that they'll have in common? You see a hydroxide at the end, so they're easy to spot. The only exception, I mentioned there was an exception, letter J. That is ammonia. It's used for cleaning. That is a base. Ammonia, it's a base. And if you're wondering, well, is it strong or weak? It's a weak base. So I'm going to put a W next to it. It's weak. All right, next, everybody else we're going to identify it as strong or weak based on where the first element comes. Remember, if it's an alkali metal, that's all the elements in the first column, except for hydrogen, then they are strong. All right, so who's strong? This is an alkali metal, so that is strong. Cesium is an alkali metal, so that is strong. Potassium, alkali metal, so it's strong. Magnesium is an alkaline earth metal, and so is potassium. All right, and all of those would form a strong base because they're an alkaline earth, except for 2. So let's review, who are they? Magnesium and beryllium. So magnesium, don't let that one confuse you. There we go. Magnesium, you say that's an alkali earth metal, but you said it was, that's an exception. It is weak. What about calcium? It's an alkaline earth metal. Yeah, that one is strong. All right. Beryllium, that's an alkaline earth metal, right? So it's a strong or weak. Again, let's go back and check it out. Beryllium right here, Sorry, although it's an alkaline earth metal, it's an exception. So for beryllium, we're going to say that is weak. All right. Now, the following, all the remaining elements, for example, here, iron, chromium, aluminum, are not alkaline metals. They're not alkaline earth metals. So therefore, we can immediately classify them as they're all weak. So that is weak, that is weak, and that is weak as well. So those are the elements that are strong, and those are the elements that are weak for bases. And again, last one, J, that's the only one you should probably memorize. Like NH3 is a base, and it is a weak base. And that's how you identify who is a strong and who is a weak base.
This brings us to the end of lesson 4 of unit 7. Thank you so much for watching.